Hello, my name is Evie, and I'm a second-year engineering student studying creative technology and design at the University of Colorado Boulder. Today's lesson is all about the thrust, weight, and control of a rocket, and I have HelperBot here, who likes rocket ships a lot, to help out. First off, why do we want to make a rocket? Well, it's typically because we want to explore space and learn more about it. As humans, we love to explore and educate ourselves about the world around us, and we can do that with exploration vehicles that engineers can build. In the past, there have been many people who were engineers or used equipment designed by engineers in order to explore. Some examples include Junko Tabei, who was the first woman to reach the summit of Mount Everest using eye protection and climbing equipment designed by engineers, or Amelia Earhart, who was the first woman to fly solo across the Atlantic Ocean with a plane designed by engineers. We also have Sylvia Earle, who dove 50 feet below the ocean's surface and lived in a small structure for 2 weeks using the help of an engineering-designed pressurized suit and underwater submersible. Last but certainly not least, there's also Valentina Vladimirovna Tereshkova, who was the first woman in space by using an engineering-designed rocket that she also worked on. All of these people wouldn't have been able to explore without being engineers or having engineer-designed equipment. So, on that note, today we'll be focusing on the basics of how a rocket works, one that can reach space. HB, do you think an airplane can fly into space? That's right, an airplane cannot fly into space. This is because an airplane needs air to fly, and there's no air in space. Airplanes use propellers and wings in order to fly, by moving air with the angled blades of the propeller, like a fan. Rockets, on the other hand, don't use propellers or wings in order to fly because, again, there is no air in space. So, how does a rocket work then? Well, these rockets use Newton's third law of motion about equal and opposite forces in order to do so. Newton's third law of motion explains that rockets can theoretically be moved in one direction by ejecting mass in the opposite direction. However, it isn't that simple in real life. A rocket is very big and heavy, so it takes a very large amount of force in order to launch rockets into space. On top of that, rockets don't fly straight on their own either. In order to design a rocket that can be launched into space, engineers must consider three main things: thrust, weight, and control. Thrust is directly related to Newton's third law of motion. Thrust gives the rocket the motion it needs by creating force in the opposite direction that the rocket needs to go. Weight is related to thrust. The heavier a rocket is, the more thrust it needs to take off, so engineers have to consider the weight of a rocket too. Lastly, engineers must figure out the rocket's control, so it can be balanced and stable, and so it can move in the right directions to safely get past Earth's atmosphere as well. First, let's focus on how thrust for a rocket works. Rockets move by expelling mass, which is the action, in one direction, to move the rocket in the opposite direction, which causes a reaction. This is called thrust force and is described by Newton's third law of motion. For chemical rockets, the action is when the hot gas propellant is pushed out of the engine. This then causes the reaction, which makes the rocket move in the opposite direction, typically upwards. Did you know that rockets move more efficiently in space than they do in Earth's atmosphere? That's because the surrounding air makes the rocket move a little slower. This effect is called drag and is caused by air resistance, which space doesn't have. Air resistance can be demonstrated by a piece of paper, here. If you hold the paper flat above the floor and drop it, the paper slowly floats down to the floor. However, if you crumple the piece of paper, it'll fall to the ground much faster. This is because the crumpled paper has a smaller surface area, so the air doesn't have as large of an area to resist the motion of the falling paper. This is why rockets tend to move better in space, because they don't have any air resistance to slow them down. Aside from air resistance, we also want to take a look at what the air inside a rocket is doing as well. For slow-moving rockets, such as paper ones, the nozzle where the air exits must be as small as possible in order to make the air accelerate faster. Because air is a gas, it can be compressed. Devices called air compressors use a pump to push a lot of air into a small container at a very high pressure. When the air is let out of the container, it blows out very hard and very fast, like when you pop a balloon. When air moves slower than 200 miles per hour or less through a tube that decreases in diameter, it doesn't compress. Instead, the air speeds up. An example of this is when you open a door to a building, you typically feel a rush of air. That's the air speeding up as it is forced through a smaller opening. Now you might be wondering, if air moves faster out of a smaller nozzle, why do some rockets typically have bell-shaped nozzles instead? This is because rockets usually travel faster than the speed of sound, and that changes how the air behaves in the nozzle. When the air is moving faster than the speed of sound, it becomes compressible and will slow down if the nozzle diameter gets smaller instead. So, a rocket moving that fast must have a nozzle shape that expands at the end instead, so the air can speed up. The weight of the rocket is the force that opposes motion and thrust. So, a heavier rocket requires more thrust to reach space. Engineers often try to find ways to reduce the weight of a rocket using lighter materials so the rocket doesn't need to use as much thrust. However, strong lightweight material can be quite expensive, and lighter rockets aren't always the best option. For example, a paper rocket wouldn't be able to make it to space because it lacks a strong structure to survive the harsh elements of space in space flight. A good engineer must come up with a rocket design that balances both the strength and the cost of a rocket. The weight distribution of a rocket is also quite important. The point where a rocket's weight is equally balanced is called its center of gravity. Have you ever tried to balance a pencil on your finger? If you've ever successfully done this, then where your finger is balancing the pencil is where the center of gravity is. This is because the weight on one side is equal to the weight on the other side. This concept applies to rockets as well. Now that we understand how thrust and weight play a part in engineering a rocket, we can take a look at the control of a rocket as well. It's almost impossible to predict the movement of naturally unstable objects, such as a football or a popped balloon. When throwing a football, the quarterback usually spirals the ball so that the trajectory is more accurate. Meanwhile, a popped balloon has absolutely no control in where the air ends up pushing it, because the hole in which the air is escaping from is flexible, and it can rotate. It is very important to be able to control a rocket before it reaches space. But how do we do this? We know that airplanes have wings, but they have smaller fins on the tail as well. Rockets also have similar small fins on the tail. However, they don't have the larger wings that an airplane has. This is because wings only provide lift that is perpendicular to the motion of an airplane or rocket, and they create drag. This is fine for airplanes that fly horizontally and have air that the wings can catch, but rockets need to fly vertically. The best way to get to space is to go straight up with as little drag as possible, after all. Airplanes get their lift from the wings, and rockets get their lift from the engine thrust. Both need the smaller fins on the end that provide the necessary control, though. Take a look at this diagram. This represents the trade-off between wing lift and drag. If an object with wings has a constant thrust, like an airplane, it can stay aloft for longer. The extra thrust helps with the drag and lets the wings continue to make lift. A wing with no extra thrust seems to do better than a rocket with fins, but because the wings create a lot of drag without any extra thrust to help out, all the forward motion is lost. This decreases the lift, and gravity quickly pulls it down. Small fins do not generate lift, but they make up for it by not adding much weight or drag and helping with control instead. Now, there is one more important point that must be considered when building a rocket. It relates to the rocket's center of gravity, and it is called the center of pressure. The center of pressure is different from the center of gravity. It is the point about which the surface area of the rocket is equally balanced on both sides, not the weight. Take a look at this diagram. For a rocket to be stable, the center of pressure must be behind the center of gravity. This means, if a rocket is pointed upwards, then the center of pressure must be below the center of gravity. This can happen by adding fins near the back of the rocket. They increase the surface area in the back of the rocket and move the center of pressure back as well. Or, more mass can be added near the front of the rocket instead, which moves the center of gravity further up towards the top. If the center of gravity and center of pressure are at the exact same spot, the object will then rotate randomly in either direction at any time. So, engineers must decide where they will put these 2 points on a rocket in order to make the best rocket possible. Now that you know the basics of how a rocket works, maybe one day you could also be an explorer that uses engineering design equipment, or the engineer that makes the equipment instead. Or both. The possibilities are endless. Anyways, that's all for today. Thanks for watching, and we'll see you next time. Check out the full lesson on the Teach Engineering website. Then, check your knowledge of a rocket's thrust, weight, and stability by building paper rockets in sprockets and thrust, sprockets and weight, and sprockets and control.